today we will be talking about deep learning. So forget the title, it's just to get you hooked. We'll look at some TensorFlow code, but it's mostly going to be about deep learning, basics around deep learning, associated stuff. This talk was first delivered on 5th of November. There have been changes. The slides, or that date on that slide has not been updated. Anyhow, so deep learning. Do any of you guys use some form of deep learning framework? Are you familiar with neural networks? Do you use neural networks for anything? Okay, cool. So this is just the right level of talk. It is very introductory. I don't know if we've got enough to fill the whole thing, but hopefully we can go into details when and where necessary. We'll start by looking at what deep learning is, neural networks, some TensorFlow, and then different types of neural networks and some concepts that go just below the surface. So we don't just do something like word count and say, hey, look, neural networks. Right. So when you hear about deep learning, what do you think? Neural network with multiple hidden layers. Cool. Where would you use it?
Recognition of generalized concepts from specific items. So this is a picture of something. So the human doesn't have to do it.
Yeah, that's a very good use case. If we were to generalize that further, the idea is that to make deep learning work, you will need lots of data, and you will need lots of computational power. And if you don't have lots of data and you don't have a complex problem, then deep learning is not the thing for you. If you have small amounts of data, it is possible to get good results, not from deep learning, but from traditional statistical approaches. Because
what would you consider small data?
Hundreds of examples, thousands of examples, not in the millions and millions of stuff. So yeah. So I mean, there are statistical models that can work with 100 data points and still give you fairly good results, or a few thousand data points. If you can compute something with traditional methods on a single machine, do it. There's no reason to go into the whole big data thing unless traditional approaches are not working for you. Okay. Right. Now, one of the areas where, or rather one category of areas where deep learning is proving to do really well is solving things that previously only humans could do. So, as you said, recognizing images. We'll look at some more examples of that, kind of like understanding text or being able to create artwork. Things that machines, when we think of what machines can do, we think that this can't happen. But these are areas where deep learning is actually producing results. And we'll look at some examples. The concept of neural networks has been around for a long time, decades, right? Back then in the 70s, 80s, there wasn't enough computational power to make this production grade, at least not generally. And the other thing was that each different industry who tried to apply it used their own framework. It was like, well, now we have Microsoft building their one, Facebook building their one, and whatnot. There is some level of collaboration, which is good. But previously what would happen is that, say, the electronics industry would come up with their own thing. People who focused on image recognition, they'd come up with their own thing, and there was no opportunity to share the tech across platforms. So people were like rebuilding the same things over and over again, even with the limited computational power they had. So it was quite impractical. Some of the changes that we're seeing now is frameworks like TensorFlow, PyTorch. These are, these share terminology, they share design principles, and shared learnings, plus they provide the technology in terms of Python libraries and whatnot that apply cross-discipline. So it doesn't matter if you are trying to predict election outcomes or predict stock trades, stock prices, or production in a plant or something, right? The same tools can be used in all of these scenarios. They'll be applied differently, but you won't have to relearn a framework just because you're crossing a domain boundary. Okay. So that brings us to neural networks. Are people familiar with something like that? Okay, it's a very simplistic thing where we have. Sorry, I have a hideous cough, and I'll be coughing. Bad for the video. Right. So the idea is that we have nodes that receive input. They do some calculation. We'll look at what calculation that is in a moment, and they emit some output. These outputs go to subsequent nodes. They do the same thing, and there's layers and layers of these until finally we get to some sort of output. Okay. Collectively, this is called a perceptron. People often use the terminology of, well, the human brain when thinking about how neural networks work. That's not necessarily the most accurate of things. Neurons in our brain, we think, work kind of similarly, as in they receive input, they do some stuff, and they relay on the output. But there are many things about our brain that we don't know. There are competing theories. There's the notion of a grandmother cell, with the idea that it can behave differently in different contexts, and based on well, what they're connected to, they can actually exhibit different behavior rather than work the same way every single time, like perceptrons do. So the notion of an artificial neural network or neural networks for deep learning, instead of the biological model, it's better to think of it as a mathematical model. And the mathematical model is extremely simple. Okay? What we have here, oh look, the cursor shows up on the screen as well. Cool. So we have an input, we have a weight, and we are doing a weighted sum. So you can see we multiply the weight by the input for each of the inputs. We sum them together, and we call a function. And that function can vary for different results, but that's kind of the model of a neural network. Oh, sorry, that's kind of the model for a perceptron in a neural network. Okay. Questions around that? Yeah.
That means it's got no memory.
Yeah.
Sorry.
There are exceptions we'll look into later. Yeah.
When you use the mathematical terms there, my math's a little rusty, but that's a sum of things. Is that a literal addition, or is that some way of combining, which varies?
It's a literal
It's a
addition.
literal addition.
Yes.
Okay.
The thing with neural networks is that they do extremely simple computations many, many times, in many parallels, and they figure out the weights. What we try to do is figure out the best weights to apply at each layer, and that's where the training comes in.
Okay. You talked earlier about how you want a large amount of computational power.
Yeah.
Is that for the training of the neural net, or for the use of it, or both?
The training.
Training.
The use tends to be less intensive.
In some sense, I might serialize my resultant net and deploy it onto a much lesser piece of hardware and use it there with some success.
Yeah, that's common across most machine learning things anyway. The training is what takes most of the power. We'll see. We do a forward propagation, then we do a backward propagation. But yeah, actually, we might not see. If we haven't seen by the end of the talk, then we'll have time to discuss, and then we'll go into more detail there. But this is literally a weighted sum. Okay, so input x1 is multiplied by weight w1. Input x2 is multiplied by weight w2. Input x3 is multiplied by weight w3. These are then summed together, and a function is called. And that gives us our output y. It's as simple as that. There's no more complications to this. Okay. Right. So first of all, logistic regression. Anybody have any idea what this is? Okay, go on.
So you calculate the probability if you put two outputs,
Yeah.
and you calculate the probability of the transition.
Yes, yes. So although it's called regression, logistic regression is actually a classification method. So you have two or more actually. You can have multiple. Potential classes, like say you're trying to identify digits from handwriting. So you have 10 classes. And you're trying to predict what the probability is that a certain number or digit is 1, 2, 3, 4, whatever. Okay. So the model for logistic regression is quite simple. We have a weight matrix, we have an input matrix, we add a constant, and we get some output. If there are curves, your inputs, you can take squares of inputs and whatnot, but at its basics, it's a linear equation. That's why. So in terms of here, what we get is a weighted sum plus a constant. We'll ignore the constant for now, because you can center your input so that that becomes 0. But that gives you an output y, right? You take that output y and you run it through this function. This function is called softmax. Okay. Why it's called softmax? Less important, but effectively what it does is instead of it having a 0, 1, it has a slope. And the benefit of something having a slope is that you can then take a derivative. If you can take a derivative, then you can run optimization on it, like gradient descent and whatnot. Okay, so whenever we see something that's like straight lines, and we're trying to use it in a learning construct, then it's better to have, instead of a kind of sudden rise or sudden drop score function, it's better to have a kind of gradual growth. And what this does is it takes our output from this equation, and it gives us kind of like a step function with a curve on it. Okay. The output of this is that we will have probabilities. So over here we had scores. Let's say wx plus b. If it were 2, 1.0, 0.1, these would be scores, or otherwise known as logits. If you take the logits and you call this softmax function, then what you get is probabilities. And the nice thing about probabilities is that if you have 0.7, 0.2, and 0.1, then you can say this particular input belongs to the first class, not the second one or the third one. Even gives you a degree.
Yeah. Sorry, I'm losing the connection between the previous slide and this one. On the previous slide, you seem to have one output, but here you seem to have 3 inputs.
So remember, here this is a matrix.
Right, so I get that you've got like a capital A there,
Yeah,
and that you're reducing that to some set of numbers or a matrix of numbers, which is then going through the function, producing y.
Yeah, and y itself will have 3, right? So this will be the score for it
so
being
it's like
A.
a 3-way vector. Or
Yeah,
something.
3-way vector. Yeah. So the reason for this is because you have x as an input, and you have 3 weights, right? The first weight, second weight, and the third weight. So the weights will multiply with the inputs, giving you a higher value for the first one, a lower value for the middle one, and a tiny value for the last one. Now, 2, 1, and 0.1 are also kind of iffy, as in like, okay, this is 2, this is 1. So it could be either the first one or the second one, right? I mean, okay, not really, but if you look at those values just numerically, because in terms of scale, this is saying 2, 1, and 0, almost. Okay, but then when you apply softmax to it, the probabilities kind of are drawn out much better. So here, this 2 becomes 0.7, which is a 70% probability, which is much more differentiative than, say, 2 and 1. Okay. So if we go back to our first function over here, that was our weighted sum. That gave us our y. And this f was our softmax. And the resultant thing we got was the final output, which is a vector of probabilities. Okay. It's not really yet a vector of probabilities, because what we then do is call a function on it called categorical cross entropy. Okay. And what this does is basically I won't go into the maths for this, but effectively what it does is whatever has the highest probability gets a 1 and the other ones get 0. Very simplistic, but at its core that's what it's doing. Okay, so instead of having 0.7, 0.2, and 0.1 to deal with, you basically get that this is an A, this is not a B, and this is not a C. Right, so the benefits of a linear, what we looked at was a linear model, right? The benefits of a linear model is that GPUs can calculate these things extremely fast. The reason GPUs exist is because they can do these calculations very fast. Okay, they multiply matrices. Your input to all GPU, have you guys worked with shaders? You have? Cool. That was back in the day. My university project was on shaders. It's like, man, that was cool stuff. But yeah, so the instructions you send to a GPU are almost always entirely in terms of matrices and vectors. Okay, and what it does very well, very fast, is multiply them together and give you some output. GPUs tend to have a lot of low power cores, and this is what they excel in. This is dedicated hardware just to do this. Okay, and as such, GPUs are very, very good at calculating the result of a linear model. Okay, it's also stable, as in it doesn't go erratically. You know, just it's like this, and then suddenly goes poof. You have a kind of range-bound level in which we're dealing with. And the other thing is, if you have a linear model, then the derivative of that is going to be a constant. Okay, so y equals mx plus b. The derivative is going to be y by x or m. Okay. The cons of a linear model is basically the number of parameters you have. Okay, having lots of parameters has a number of problems that we'll get into a bit later, but at its basic, it's the more parameters you have in your model, the more things you need to train. The notion of training a machine learning model is basically taking those things like weights and finding the optimal value. And in our case, you have n inputs, k outputs. This is something you're going to have to train. This is something you're going to have to train. And the model now has sorry, n plus 1 times k parameters. So this is one downside of having that. The other problem is that it's linear. So if the relationship between your inputs and outputs are linear, then great, it works. If there's like curves involved, like most real physical data, then linear models don't work very well. Now, if you apply this function, the result is also going to be effectively linear. As in, when we say linear, we don't necessarily mean it's going to be exactly a straight line. We mean that in terms of the input and the output, the degree of the input. So we're not taking squares of the input. We're not thinking about relationships between the inputs. So for example, if you have two dimensions, like say, I don't know, a person's age and a person's salary, you're not considering a relationship between them. You're treating them as independent inputs. That's what a linear model is about. Okay. And this is basically what that's saying, is that if you have x1 and x2 as two separate things, and you can have many, many more of these in your model, that's still a linear model. But if you have any interaction terms where inputs tend to be the multiplication of the two, for example, then those sorts of interactions can't be captured in a linear model. Okay. Right. Till now, what we said, there was very little deep learning. This is all basic stats. Okay. So one of the inventions, I guess, not really inventions, but one of the things that really made deep learning take off, because it started doing really well for nonlinear functions. Okay. Now, if your nonlinear function is very curvy, that's still very difficult to optimize. Okay. But this little thing, or the reticulated unit, it turns out it performs surprisingly well when you have lots of data. Okay. All it is basically it's a function that up until a certain value, it gives an output of 0, and then it becomes linear. Okay. And it turns out that a lot of nonlinearity can be captured by repeatedly applying the same thing. And when you're training neural networks, you are repeatedly applying the same thing. So it was more of kind of like, hey, let's do this. Maybe it'll give us something, and they did, and it did. And values are one of when you want to introduce some sort of nonlinearity in your module. This is one of the things that work, okay, very nicely. And because they're so simple, this is still very fast on GPUs. You're not calculating squares. You're not multiplying stuff together. It's still basically do a check. Is the value greater than, say, in this case, 0? Yes. Then calculate the linear value. Otherwise, just take 0. Okay. And the deep part of deep neural networks comes from basically creating these in layers, many, many layers, one after the other, and more and more and more. So, for example, we have a linear model here where we have a linear layer. We're doing a weighted sum, but then we're adding a bit of nonlinearity. And then you can do another one, and then you can do another one, and you can do another one. And you can make it a lot more complex than simply say, multiply by W and add B.
Yeah. So that prelude, is that making something non-linear linear or something linear non-linear?
It's adding nonlinearity to your model.
Regardless of whether it's...
Yes. So one of the things that neural networks do, and this is actually kind of might sound surprising, because in traditional statistics, one of the key things that you do is basically feature engineering. You spend a lot of time trying to figure out what your features are. You then multiply weird things with more weird things to trying to, like, you multiply age with salary, and then try to see if you can generate a feature from that and see if that's related to some sort of output. And that takes a lot of time, right? Some deep learning enthusiasts, they literally use the tagline that architecture engineering is the new feature engineering. Their notion of architecture is this, not your software architecture. Okay. The idea is that given enough data, your neural network can learn the features. You've got your inputs, you've got your outputs. If you build a relatively good model, and then you can, you experiment and you train and whatnot. But what happens is that the network itself learns, and that's the deep learning part, it learns what things to emphasize on and what things it needs to ignore. And you as a statistician or data engineer or data scientist, you don't have to figure out those things to a certain extent. It can still help. Okay, I'm not giving it tons and tons of irrelevant stuff. But then it fairly quickly learns how to ignore things that don't matter.
So if we give it, the appropriate kind of neural net with the deep learning and what have you in it, huge amount of lists of people with 10 different attributes amongst them, one of which is a goal of max salary that they happen to be getting paid, and we train it through on this, it will determine which of those attributes is at all relevant.
Yes.
And discard some of them.
Yes, but you won't know.
You won't know it's actually done.
Yeah. So that's one of the downsides of neural networks, is that they work very much like black boxes. There are some, even ongoing research into trying to make them more understandable and give you more feedback as to how they're working. But yes, in that case.
So if I've done that, if I've fed a huge amount of data through, and the neural net has determined for itself that these particular factors just not relevant to the goal of maximize this.
Yeah.
How then can I use that?
You have a trained up model as your output. So
my point is that if I come along with a new person with fresh data that it's never seen before, and I'm going to ask it to predict the salary in this case, but without that piece of information present, it will give me hopefully a fairly accurate answer based on its learning that it's done so far. It will do so using the historical learning that it's done.
Yes.
Okay.
So when we say learning, what we're effectively saying is that the network will teach itself the optimal value of, say, W and B, and it will have these constants. So when you're trying to predict with the new input, it's just doing a forward run.
So does it actually become more efficient? So on the first few thousand tries or whatever, it may well have been analysing everything that was going in.
Yeah.
But when it comes to deploying the fully trained network someplace, it will not just be more efficient because it's done the learning, it will do so because it will bypass the part of it, the analysis that ever involved looking at that attribute.
Kind of, but not really, because in terms of predicting, what it basically does is it will literally run the same computation. It's not intelligent or clever in that respect, right? It will basically take the weights it's learned, multiply the input, right? If it has deemed that a feature is unnecessary, the weight for that input is going to be 0 or very low.
Okay. But then implementation in a, well, I admit this is abstracting a lot, but certainly functional languages can not bother to multiply by 0 because they look at it and go, well, I know what that's going to be. I won't even bother following that branch. So actually, if you combine the learned knowledge with some of the optimizations that things do, potentially you do actually sort of seal off branches of computation because you just don't have to follow.
You could, but considering that a lot of this happens just in parallel anyway, so doing it for one feature versus 10 features, it's not more work because everything's happening on the GPU in parallel. It is more work, it's wasted work, but it's not, I mean, you wouldn't be saving too much in terms of computation in that regard, but who knows? Okay. Right. So the values here, what I would do is, for example, nonlinearity, as in if there's no linear relationship between one less input and output, or even there's interaction terms between two different features, then that's what values will capture, right? We'll look at some TensorFlow code. When we look at it, you'll see that you're not figuring out much in terms of inserting a value. You just say, I want a value here. Okay, and it puts a value there. It's not your job to train it because the network itself will train itself when it goes to train. Right. So TensorFlow is well, Google's deep learning toolkit and whatnot is very good. It's also hideously painful to code for. Yeah. There are frameworks on top of TensorFlow, TFLearn being one. They make programming with TensorFlow easier and cooler. It's not that they're any less efficient than TensorFlow. They're just, think of them as library functions or working with TensorFlow as opposed to, you know. You could do the same things low level by yourself if you wanted to, or you could use TFLearn and make your job easier. Okay. So this is kind of how we load data in TensorFlow with Python. I mean, most people can read Python, right? Executable pseudocode and whatnot. Okay, so MNIST is a data set that comes as part of a lot of machine learning framework things. It's in R, it's in TensorFlow as well. So MNIST is basically a handwritten digit library. So basically, you have tons of digits that have been written by hand, and they're labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. The goal of your project when working with MNIST is to accurately and correctly predict what a digit is. Okay. Here, what we're basically doing is we're loading the sample data set into training of inputs, training outputs, test inputs, and test outputs. So we're separating our data that's been given to a training set. We'll train our model on our training set, and then we will test it on our test set. Okay. Not doing validation. Okay. This slide is slightly less interesting. All it's basically doing is taking the data that's there and printing it into an image. So this is what our input data actually looks like. Okay, the function is not important. What our input data looks like, it's a two-dimensional array where certain bits are lit up and other bits are not lit up. Okay, it's black and white. That's what our input looks like. This is what's given in a 2D array to our input, and From here, we are supposed to predict that that number is 7. Okay. Okay. So in TF-Learn, this is actually a model. So ignore that. That's a framework thing, but you always do that as a first line. It basically clears out any variables from your previous run, kind of. Next thing we're saying is that we are creating a neural network with one layer, which is our input data. Okay, does everybody understand that bit? Okay. Then what we're doing, and look at the lovely mutation. Any functional programmers here? I'm actually a functional programmer, I love functional programming. But yeah, we're mutating stuff here. Deal with it. We're not really mutating, we're just reassigning. This could have been called net2, net3, whatever. Okay, we're being lazy. So the first thing we're doing is we're taking the input data and we're creating a one-layer neural network. That's our first layer, that's our input layer. Okay. Then we are adding a hidden layer by saying we want a fully connected layer. The input to that is the previous one. The activation function that we have is a value. So the f that we're doing, instead of softmax, is going to be a value. Okay. And we want it to have 128. Our input has 64. The output of the first layer is going to have 128. So we're increasing in that case. We could have made that 32. We could have made that 512. It's entirely up to us what we do. Okay. That's our definition of the architecture. We're saying the first layer has 64. How many other is the next layer going to have? We take that and we add another layer. And let's say we have that one is going to have 32. And then for the final one, we're going to have 10 as the output, because 10 digits, right? And for the final one, we can do different types of activation functions internally, but for the final one, we're going to use softmax. Because at the end of the day, what we're interested in is the probability of it being 0 or 1. So the f we talked about, that f is basically that third parameter there. Okay. So what's your input network, how many outputs you want, and what's your activation function? Quite nice. Right. So that is effectively our definition of the network. That's defined. The next thing we're saying is that we're going to run a regression. We are going to use stochastic gradient descent. Yes, it's a magic term, and they use abbreviations quite a lot. And the learning rate is going to be 0.01. And the loss function we're going to use is categorical cross entropy. So the thing we applied at the end of the f to get 0 or 1, kind of. How you calculate loss effectively. Let's ignore this. This is basically what we do for any sort of machine learning. So whether you're using scikit-learn, you will have an element of this. Okay. So what we're saying is that we're going to take this network and we are going to run a regression. It's probably better not to call this net, but hey, whatever. And then what we're saying is we take this output from regression and we tell TF-Learn to create a deep neural network, and that is going to be our model. Okay. Imagine having to create this with even basic Python or anything. That would take weeks. Okay. That will take weeks. This is why these toolkits exist. These problems are so common that if you're using deep neural nets, your concern should be these things. Your concern should never ever be, how these things are implemented.
Yeah. So using the term deep neural network, am I right? You've just got 4 layers: the input, the output, and the 2 hidden layers. So is that common these days? So these days, would you typically have many more layers?
So interestingly enough, for the majority of things, you don't need that deep of a network to get satisfactory performance. Okay. That said, we'll look at some examples, and yes, they can get pretty deep. Okay. If you're looking to win competitions, they'll get very deep. We may cover this when we go to overfitting, but having it too deep can be counterproductive. Your network might get too good at learning your data. So it's a trade-off. So the next thing we do, we have our model, basically fit it by calling model.fit, surprisingly. And what that does is it takes your training data, takes your training output, it says how much of the data you want to hold out as a validation set. Show metric, this is for logging output. What your batch size is, what your epoch is, and what it does is it then goes and does the forward run, back propagation, forward run, back propagation, until the model has been trained up. Okay. And when does it know? When at each iteration it can improve by 0.01, for example, here, right? And at each iteration it knows how good it's doing or not based on whatever the loss function is. Okay. So sorry. Once we have our trained up model, what we can then do is basically use our model to predict on our test set, test input, and then we measure the accuracy to say, how accurate this is or not. Okay, so this is very similar to what you'd be doing in any sort of machine learning library. So whether that be scikit-learn, the notions of model fit, predictions, calculating accuracy, it's exactly the same steps. What Tensorflow and TFLearn is giving you is basically a very friendly toolkit by which you can take those concepts and apply them to deep learning, or apply deep learning to those problems. Right. So one problem with deep learning is that it learns too well. In fact, very early on, one of the biggest challenges with neural networks is that they learn it so well that they basically memorize the data. So it works very well on the training data. As soon as you give it data that it hasn't seen, it falls over because it's completely tuned to your data. So what we try to do is we prevent it from learning too well. So there are some ways of doing that. The first one is called L2 regularization. Things like regularization is kind of it's the same with machine learning. You kind of with things like random forests, you have to stop. You can't keep on having it get better and better and better, because if it does, it overfits your data. What L2 regularization does, it's some math there, but I won't go into the math. The simple thing is that it penalizes for weights. So the more weights you have, the more penalty you get. So if your model is going to learn with, say, 2 weights, and as such 2 features, and it achieves kind of similar results with 20 features, then L2 regularization will penalize the second model and reward the first model. Or not reward, it will penalize the first model less. Okay, so if you can make do relatively well with fewer features, as opposed to having lots and lots of features, then L2 regularization will kind of give you that. Okay, and the benefit for that is that because it's using less features, it tends to not overfit your data. Because if you keep letting it going, it will just kind of completely fit all of your input data, and your kind of curve would effectively look like very, very haphazard type of jumpy curve. Whereas this kind of applies a sort of smoothing, because the model will have to achieve the best value possible. And the more features it tries to do, the more kind of sharp turns it tries to take on your curve, the more it gets penalized. So at some point it reaches equilibrium where it goes like, okay, this is good enough, I'm going to have some loss, I'm going to accept that loss, because if I try to reduce loss to 0, then I will not generalize. One of the biggest problems in machine learning is generalizing models. Okay, so regularization is one thing. The other thing, and this is like only for, works for neural nets, is dropouts. So what it does is that at each stage it randomly drops half the connections. Okay, so basically what it tells your model is that whatever it learns, it has to kind of get corroborating evidence from multiple sources before accepting it. And so just something saying one thing, I mean, if you see some news on InfoWars, then you think it's fake. if you see the same thing being repeated on BBC, CNN, Fox News, I don't know, but a lot of sources, then you have more trust in it. What this is effectively doing is, for any news item, it's randomly taking out half of the sources and only letting the model learn if the remaining sources do kind of have similar inputs to it. Okay, so it makes your model robust towards flukes and sudden things happening, and as such, it prevents overfitting. And dropout is actually one of the most effective techniques for regularization in neural nets. Works surprisingly well. And if you you can drop different percentages, it doesn't have to be half. But if you drop half, then later on when you try to do sum, you don't have to do certain calculations. So it's more efficient to actually drop 50% than like 70% or 20% or whatever. Okay, right. So the next thing we're going to look at, we'll look at some categories of neural networks. First one is convolutional neural nets. Right. So have you guys seen any movies where you see like this thing, like robot or something that scans people with laser beams, right? So that's basically what convolutional neural networks are. Okay. And surprisingly, those things are not completely made up, because that's how you actually do image recognition. So before going into how they work, the thing we'll talk about is statistical invariance. Okay, that means is that let's say you'll have some attributes that, regardless of those, some things are going to hold or not hold. So, for example, regardless of color for the first one, you can say this is A, this is A, this is A, even though they have different colors. Okay. Similarly, this is a cat image. Oh, rather, this is an image of a cat, and this is an image of a cat. Okay, they've been rotated, translated. So they've been rotated. This is like 45 degrees that way. That's 45 degrees that way. They've been translated. This is the top left. This is the bottom right. But any good image recognition thing should be able to say that this is a cat and this is a cat, right? Okay. So when we say when we talk about invariance, we mean that regardless of these translations, these rotations, these two are effectively going to be the same thing. Okay. So what convolutional neural networks are is that they're neural networks that share their parameters across space. So any parameters that are for this cat are going to apply to this cat, even though they have been rotated slightly. Okay. So what a convolution is like, let's say this whole thing is an image. A convolution is basically a subset of that image. Okay. So what we do, let me just check if that slide is there. We're getting deep. Okay, right. So what we do is we go, let's say our image is this big and our convolution is this big, right? We go one at a time, like this, across the whole of the image, and we extract some outputs from each of those. Okay. Our first image starts off as a big, thin thing. Okay, thin as in it can have 3 features, maybe 4 features, R, G, B, A. Okay, so the base image, our input layer, can be what's it called? Can have 4 features, R, G, B, and A. What we'll do is we'll take a subset of that image as a first convolution and take some output, but that output is going to have a fewer total number of outputs. So instead of all of the pixels in the image, that will have a subset of that, but the output will be thicker or fatter, as in it will have more features. So instead of having R, G, B, and A, it will have some sort of thing that, well, additional outputs basically. Okay, so we're going from one big thing to a smaller layer that is fatter. Okay, and we keep on doing that. So from the first one, we have the second one, then we have the third one, we have the fourth one, and then you'll see that as we go along, we can feed the end result to a classifier, and that's what convolutions are. Okay. skipping over some details, but effectively that's what we're doing. That's how computers recognize images. They scan the base image, square by square, and generate some outputs from that, and then they analyze that, and that, and that, and then finally send the result to a classifier. So in terms of stride, a stride basically means how much you're jumping from when you're scanning the image. So let's say if kind of like this, you're going like along this dimension, you're taking that, how far you're progressing for each, right? It's kind of an example. If this phone were a tablet, then this would be a better example. Okay. What pooling basically means is that from those things, you're doing some sort of aggregation, like a max or a min or something. Okay. Less important, but the key thing is that an actual image recognition thing is kind of built up like this. So you have a base image, you have a convolution layer, you have a max pooling layer, which means for each convolution you're taking the max value. You have another convolution layer, you have a max pooling layer, you have a fully connected layer, and then finally feed it to a classifier. Okay. The details of the convolution are less important here, but if you look at the similarities between this and the code that we had, where we just went fully connected, and then a softmax, right? Yeah.
What do you mean by fully connected?
Oh, fully connected means all the inputs are connected to all the outputs. Okay. Should have mentioned that last time. Anyway. Okay. So here, previously we had a very basic linear regression model, right? A linear model that could try to predict some stuff. Now what we have is a model that has two layers of convolutions, each with max pooling, and then doing exactly what we were doing before. And this is how neural networks can get deeper and deeper and deeper. Yann LeCun, anybody heard of Yann LeCun? He's basically the head of, he's the guy who started Facebook's AI stuff. He's head of that department currently. And so there's an image recognition competition that happens every year. And people try to make better and better models in order to be the best classifier and whatnot. So a few years in 2012, the winner was Alex Krzyzewski, and his network was AlexNet. The projector isn't doing that image that level of justice, but you can see that like these networks, they have like hundreds and hundreds of layers. Okay, they get quite complicated.
Excuse me, the competitions. What, say in '98 you managed to recognise every letter. In successive years, is the competition doing more quickly or with less?
They may have more input sets. It's not just letters, it's like image recognition. So like recognizing pigs and animals. And
so the competition involves it itself.
Yeah. And yeah, I mean, every year the models get better. It's remarkable what they're currently doing. I mean, if you just look at your phone and you know what your phone can do now versus say 2 years ago, you can kind of get an idea of how it's progressing. Okay. So I guess because we didn't go into details of convolutions, going into details is kind of hard. But the idea is that from k by k, we end up with a 1-by-1 convolution for things. And 1-by-1 convolutions can be useful for adding some level of nonlinearity. Won't go into the details of exactly how. Not really important in this case. But it's worth mentioning this. This is what's called an Inception model, because everybody likes to hear the word Inception. What is Inception? It's a cool movie, though. In neural networks, what it basically means is that you take something like a 5x5 convolution, 3x3 convolution, 1x1 convolution, and just stack them together. That's all that is. Okay. So in this case, we're taking 1x1 convolutions of the raw image. We're doing an average pooling. So from this 1x1, we're then taking a 5x5. We're taking the output of that and plugging it here. We're taking the 1x1 and putting it there. We're taking a 3x3 and plugging it there. We're just increasing the thickness. You'll notice that all of these things, what they're doing is starting from some big rectangular thing and gradually shifting towards smaller, fatter things until you're increasing depth and you're reducing surface area. That's the goal.
Seems rather arbitrary.
When you send a thin class, a fat kind of small surface area thing to a classifier, it performs better than if you were to send this.
Maybe I just missed the convolution piece, but it seems like a kind of a narrowing of focus. Now, if I start off with big picture with cat in the corner, I'm hoping that the system would deduce over time that actually I want to focus on this area for the classification. But doesn't that mean that I have to effectively take a sample size, so as you say, a smaller rectangular surface, and there is my example, but then for all I know, because I haven't analysed the image yet, there might be one over here and one over here, so I've got to do that all over the place and then decide that some of these just don't matter. They're statistically unlikely to have anything in them.
Right.
Now, so if I find two,
are
you saying that I'm literally going to stack those in serial going through?
Yeah, kind of. It's kind of like what's it called in machine learning? Oh God, the word just completely gone from my head. The idea is that you're effectively getting multiple models to predict the same thing and then taking their agreement.
Okay.
Okay.
So what you get?
Ensemble models, yes.
When you get, I mean, let's imagine a 3x3 grid, the bottom left corner of which is a cat and the rest of it is sky. Don't you get 8 sets of sky and therefore there can't be a cat here?
I'll stop you there, because what happens is that the first layer, it just understands lines. It doesn't understand the shape. Okay. The layer after that puts the lines together and understands basic shapes like triangles and whatnot.
So you're talking content versus no content initially, then worrying about what the content might be.
And as the layers progress, the end result over when we get to this part is basically, is it a cat or not a cat? Over here it might be the face of a cat. If we had more layers, let's say where was Alex's thing? Yeah, there you go. So over here, for example, it might be cat or no cat. Over here it might be a face of a cat. Over here it might be lips, ears, whiskers, and whatnot. Over here it could be triangles and circles and ellipses. Over here it could be just straight lines. And gradually, at each layer, it adds more understanding. That's kind of how it works. Right, so the next thing we'll look at is recurrent neural networks. So whereas convolutional networks are invariant in terms of transformations, recurrent networks have an element of time. Bad picture that. So the idea is that in addition to having inputs and outputs, each one effectively has a feed into the next one. This is time, this is not features. So x1 and x2 are not two different features. This is x1 at t1, this is x2 at t2, or the same input at t2. Okay. The idea is that in addition to output, you feed something more that you pass on to yourself in the next layer, next iteration. So kind of like memory. We'll get to what that means.
So is that purely abstract? This is 1 second more than the previous thing you looked at, or is it the result of the previous thing in conjunction with that knowledge?
So,
because for example, if you had a video and you're looking at the individual frames of that video, several of them might appear to be blurry on their own, but taken in context with the others, you can.
Kind of, not the blurry bit, but let's say another word for RNNs are sequence models. So basically, the sequencing of things becomes important. That's effectively what it is. Okay. So basically, what you have is a level of feedback. So previously, your output was based on your input and your weight, and that was it. Now your output is based on your input, your weight, and what happened before, the last time. Okay. Now the problem with that is that your gradients can tend to explode, or it can tend to come down to 0, because you're reinforcing the same thing over and over and over again. Okay. The way we get around exploding gradients is very easy, is that you have a maximum clip. So if it reaches a certain value, then you just clip it. For the other one, we have notions of what they call long short-term memory. So why they call it long short-term memory, or LSTM, is basically the memory you have is that you don't let it go on for a long, long time, but you have a limited amount of time, limited amount of memory that you can remember much later. So think of it like if you think how your own memory works, you may remember something from childhood, right? Maybe you went to play in a park or something, right? And you can remember like a 5-second clip of something that happened. Okay, you don't remember what happened before it, you don't remember what happened after it. Certainly not everything that happened subsequently. You just remember those, 2 or 3 minutes that something happened.
So long-term, short duration.
Yes. So that's how you get around the vanishing gradient problem. Also the exploding, it works both ways, it takes care of both. So LSTMs and RNNs, in terms of regularization, this is kind of more around implementation. But L2 regression works quite well. Dropout, you have to be careful. As in, if you do dropout on inputs, that's fine. If you do dropouts, you can't do any dropouts from the past value, because then the meaning completely differs. As in, you're not dropping input sets, you're dropping what you told yourself from the past, which can be bad. Okay, we'll not go into beam search because that's not that interesting. We'll look at some applications of, yeah, that's impossible to see. We'll look at some applications of RNNs. So in terms of convolution neural networks, there are many applications, but they primarily tend to be around image recognition. So identifying cats and dogs, that's like the hello world of deep learning. You have a set of cats and a set of dogs, and you have to say which is which. But RNNs can do some pretty cool stuff. Okay, we can't read this, but take my word for it. This text is actually very nicely summarized by the bottom. So this blurb is summarized by this blurb. You can't see either, so yeah. But it does a pretty good job. Let's see if this works. Right, so that was actually entirely generated by an RNN network. Okay, and there's some music that you can find on YouTube. That's basically people who've built neural networks that are generating music. They were given samples. In this particular case, they actually used Beatles music. I personally think it's more like Beach Boys, but hey, and that's what it produced. It wasn't like humans helped it in any way. They just gave it samples and said, hey, go make another one. Okay. Another one that we can hopefully look at, if I remember my, no, what happened there? No, can't have this. There, okay, yeah. We're here, right? Okay. So next thing is, this is from some assignments that we were doing as part of a Udacity course. That is not important, but effectively what we're doing is we are feeding we're building a recurrent neural network there, and then we're training it on the text from a lot of Simpsons episodes. Okay, and then we are telling it to generate some output. Yeah, the TV script is nonsensical. In many ways, the Simpsons are nonsensical. But this was basically a very simple model that was kind of used in teaching neural networks to people who have never used recurrent neural networks before. And that's the level of output it actually got. And if you think about it, yeah, okay, it's kind of random in terms of overall context, but the sentences, they kind of do make sense. They're not completely, weird. So text processing is one area where neural networks are actually quite useful. You'll see these are not actually copied and pasted or cut and pasted excerpts from whatever it was fed. It was actually trained on it, and it actually generated these things. Yeah.
How do you distill? I can understand how you can distill an image down into numbers, but how do you distill the text into numbers?
Ooh, that's the whole. NLP is a whole different field altogether. There's things like vectorization. You can at the end of the day, you convert it to vectors. Okay. So one of the things, let's say you have a word with, say, 5 characters. It could be that you take, it's called shingling. Basically, you take 3 characters. That becomes an identifier. And the next 3 characters becomes another identifier. And the third 3 characters becomes another identifier. Okay. So your 5-letter word becomes 1 shingle, 2 shingle, 3 shingles. Okay. Each one can have a 0. In this case, it'll be 1, 1, 1. Okay. You'll have many, many shingles. And then other words will have, 0, 1, 0, and whatnot. But at the end of the day, it's going to become vectorized.
So each word gets its own fingerprint, effectively.
Yeah, effectively. I mean, that's one of the more advanced models. The very most basic thing is bag of words. As in, you just say a word count. As in, this document has this many words. That's it. Has these words this many times. And then you add things like sequencing, you add shingling. Shingling usually results in things being massive, so you then have to hash them into buckets so that you can compute them reasonably. But NLP is like a really, really interesting field, because if you think images have high dimension, NLP has much, much higher dimension. Right, so script generation, language translation, this should be fun. Who knows French? Okay. So this is basically, I'll give you the links to these or tweet it out. You can look at the source code for all of these, as in what it's doing. And you can see how the model actually trains itself, right? For example, for epoch 0, you can see how many batches it's processed, what the training accuracy is, what the loss is. And you can see the loss gradually going down, down, down. It's down to 10%, down to 6%, down to 4%, down to 2%. And whatnot. Okay, I think it comes down to 1.5%. So at the end of the day, after all that training, we give it to things to translate. Oh, Jesus. Yeah, so we say, he saw a old yellow truck. I don't know French, but I am told that this is fairly accurate. Right, this is quite interesting. Autoencoders basically use kind of like a feedback loop, and they can be used to, well, not really a feedback loop, but effectively what they do is they fill in missing data. Okay, they train itself to fill in missing data. And somebody had the bright idea that, hang on, if it's filling in for missing data, we should be able to make blurry images sharp. And there's actually a website now called let'senhance.io. And if you go and submit your horrible holiday photo, it actually makes it sharper. I don't know if it's visible, but you can see that this image is quite hazy, right? And the sharpness here is noticeably increased. Okay. This thing hasn't been trained on what that place looks like. It's been trained to recognize where things are blurry and how it can be filled in.
Where do you get sample data to start doing that?
Generate it.
I was wondering the same thing about the English to French translation, because anything.
Oh no, the English to French is very easy because you have like lots of translations to. So basically, in that case, we're not using any external model in that case. So you can go and look at the code. We've just fed it some paragraphs of English text and their French translations, and it's gone and generated that.
I just figure it must be hard to come up with quite so much of that data, because where do you go for an okay.
If you Google, use your
Yeah, that's the problem. You're using one AI to train it.
Oh, there you go.
My images go onto the Google Cloud, and it's entitled.
All right. So if we're back to images, right? You give it a sample image, but you don't give it the same image more sharply for it to know how the
Yeah.
distinction was made.
So you can,
Take a sharp image to make it blurry.
you can
Oh,
inject.
you
Yeah.
wreck it rather than make it better. I suppose that works. Yeah.
Actually, that's how they. For images, that's actually how to do it. It's kind of similar to how you simulate faults on networks. For software that needs to be, reliant on network faults. Right, style transfer. This is one of the coolest things. This is actually a website where you can do this, and you basically give it a picture, and you give it another picture, and it takes the style of one picture and superimposes it on the other. Not really superimposition really applies that style. It's quite cool. You can go and play around with it yourself. The code for it is actually out there. For when you want to, we're talking about Gary Short and political statements. If you want to superimpose cabbages onto cabbages, but that's pretty good. I mean, look at that. Look at that, and then look at that. It's uncanny.
Which one would you vote for?
Right. One of the biggest advances in recent times is actually GANs, generative adversarial networks. And how GANs work is that there's a neural network that's generating stuff, and another neural network that is discriminating stuff. So it's basically two neural networks who fight against each other. And what the generative network does is, starting from random blurb, it just generates data. Okay, and what the discriminator does is, given some real data and the inputs from this, it decides whether the thing that's been generated looks like the real thing or it's a fake. They're competing. This guy is trying to create fraud stuff, fake news. This guy is trying to identify fake stuff, fake news. As soon as this guy gets better, this guy has to kind of get better after that. As soon as this guy gets better, this guy has to do better. And it's like competitively, they get better and better and better, until what happens is that the things that are being generated are so much like real data that it's very difficult to separate the two, even by humans. Okay. So StackGAN is one such model, and this is actually a real application now. You can go to that website and you can type in descriptions. Okay, so if you were to type in, this small bird has a white breast, light gray head, and black wings and tail, the GAN will go and draw you this image. This is not an image search. Okay, it's not doing this from a library of images. It is drawing a picture of a bird with that description. Okay, when I said that things that people could do and machines could never do, this is like GANs are one of the main areas where this is happening. It's kind of almost scary with what's being done with these things. There's also Pix2Pix. That's also quite cute. Basically what you do is you do a doodle, and it makes cats out of it. Again, this is not an image search. This is literally, that image is generated based on what's been drawn here. Just search for edges to cats. And it sounds fun, but you'll actually see that even some web games these days, they have things where you can basically draw a line, and that's so like previously you had lemmings where you click and basically go okay, walk along this bridge, or do this and do that. Now you can literally draw a line, and the characters kind of walk along those. Okay. Anyway, cartoon faces. Who's got a cartoon avatar? There you go. That's actually a GAN in action. So you feed it a photo and you get back a. This is actually interesting. Cycle GAN. This was kind of remarkable. The reason this was remarkable was that, let's see, do I have a video for this? No, I don't. So what it was given was basically a lot of pictures of horses and zebras. It was then given a video of a horse running around a field, and it generated a video of a zebra running around a field. This is actually so good that let's see if I can actually find it on YouTube. Yeah, I'm into scuba these days. Yep. So that right one is generated by a computer. There's some weird shit on YouTube, I don't know why. Anyhow, right. One practical use case for this is actually in generating training data. So this is actually used for a lot of gesture control type things to identify software that identifies where you're looking. Okay. Now it's incredibly wasteful to actually have humans look that way, that way, that way, that way, yeah, and capturing images and use that as training data. So what it does is basically you capture some of that data and you capture a lot of people and you let the GAN generate the remainder of your training data. Yeah. So that another machine can train itself on recognizing where you're looking.
How do you train the generative neural net on the correct generation of data?
Well, it just goes and generates, right? Eventually it becomes correct. That's the idea.
But you have to measure it against something to determine.
That's the discriminator that's doing it. So instead of a human trying to figure out when the model is good, there's another neural network who's in.
Yeah, but if I start with 1 million samples, right, and I feed that into a generative set and I get eventually 10 million samples, those extra 9 million samples are derivative of my first set. So what makes it any better to train the discriminator based off the 10 versus the 1?
No. For the discriminator, you give real data.
Sorry, I meant.
The generator starts off with random fuzz.
So, sorry, training the discriminator from the 10 million rather than just the 1, since the 9 was generated from the 1.
No. So if you look at the generator, it doesn't have real data as input.
None at all?
Not at all. Or at least not the set it's being tested. At least not the set it's being trained on. You could give it some other data. But, sorry, not the set that is being discriminated on. That sounds weird. Not the input data for the discriminator. That's never shown to the GAN.
Must have feedback from the discriminator to know how well it's done.
Yes.
Yes. Right.
So the feedback it gets is, yep, this is, I think this is real news. I think this is fake news. That's the only thing I'll get. Right. Imitation learning that's another use case. It's basically like where systems try to mimic other systems, and you can see how GANs can be useful that way. Particle accelerators is also kind of an interesting application. So basically they use GANs to generate, have you guys ever heard of what's it called, Monte Carlo simulations? Basically you just throw random shit and then see what sticks, kind of, okay. Particle accelerators, kind of, if you were to run the experiments for each and every one, they would become prohibitively expensive. So what they do is they use the models to figure out areas that are of promise and then narrow down their areas of research. And GANs are helping in that regard quite a lot. Captures and how capture breakers, they're also kind of based on GANs these days. And this was actually our last experiment for that particular course. The idea was that we generated a GAN and we gave it a bunch of human images. Well, first digits and whatnot. But at the end of the day, towards the end, we gave it a bunch of human images to train on. I don't know if we're showing them. No, we're not. Okay. And over many, many iterations, you can see that the faces, so this is the output of the generator, right? From random noise, effectively, almost. And then gradually it gets worse, it gets worse, it gets worse, and then it's starting to get better, 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 and it starts resembling some human faces. Not high resolution HD, but I mean it's a 32 by 32 image.
So to do this, is somebody basically, so it generates noise initially, you go, that's not really a human face, then generates something else, it looks a little bit more like, so you say yes, 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 no, 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 and you're just sending it along a path where eventually it's creating stuff like this.
Yes. Scary, huh?
How does it handle change and whatnot then? And surely this is just going to keep, you're going to get more of the same. So how does it handle like mutations?
What sort of mutations?
Well, I'm just thinking.
So remember,
from a evolution point of view.
So one reason for starting from, say, random noise is that it has no bias towards what a human looks like. It doesn't know it's generating humans, right? The fact that it's generating humans is because the discriminator was told that the target looks like this. As long as it's vaguely similar to any one of those, the discriminator is going to go like, yeah, you're making improvements.
Now how would it handle it if humans evolved and ended up with two noses? Would it then just fall apart? Or would it generally...
That depends on what input you're feeding to the discriminator. If you start feeding input with humans with two noses to the discriminator, then it will say...
So it will adapt over time?
Yeah. Right. I mean, you'll see, previously it got worse before it got better. And certain iterations is going to try other things, and it will
Is each iteration informed, yes, this is better than what you had before, or this is worse? At what point will it then be considering its outputs? I mean, I'm trying to think. So towards the end here, there's a lot of them which we would recognise as facial in appearance, right? Yeah. But the first two or three were nothing like that, and yet I would still have told it this is more like a human. So at what point will it look back on its history and go, actually, no, that got me where I am, so that now the bulk of what I produce is here, but actually that wasn't a human. Right. So how does it...
I guess
are you saying closer or further away, and then finally yes and no? Is there a distinction between that kind of feedback?
It depends on how you build the discriminator, really.
It's a long-term, short-term thing. You forget, I suppose. Yeah.
Are you saying like if you go too far down a branch, you're trying to get back?
Well, you start off with something that's just fuzz, so I say no, that's not human. The next randomly generated thing has fuzz with a greater density where a face or a nose might be in the middle. And whilst I say yes, that is better, and I'm improving the algorithm from this point onwards, going down that sort of path, it shouldn't be used as an example of actual success, if that makes any sense. So it's better, but it is not right.
Yeah.
And that's...
Also, one of the things is that discriminator is not static. It's also improving at the same time, right? So, for example, you could start feeding it more training data as things go on and get things more accurate and whatnot. So the discriminator itself has to be evaluated as well, right? Normally they evaluate each other, as in if the discriminator sees that too many things are being okay, then it knows that it needs to make itself, more stringent in terms of quality control. And at that time, the generator starts failing again, and it makes itself better. So they don't let each other have an easy time of it.
Do they not eventually settle on an equilibrium?
Well, if they settle on an equilibrium, then what does that mean? Does that mean that a lot of things being generated are being passed or failed, or? That said, I mean, GANs are so in terms of computational research, GANs are extremely new. They're like within the last 4 or 5 years. This is like open research right now. Okay, and a lot of these real applications that we're talking about come from GANs, so they're incredibly useful.
Is there a feedback from the GAN to the discriminator? So if the discriminator says, "Yeah, that's real," is there another feedback loop usually where the GAN can actually go or wrong?
I guess you could have. That's a question for Ian Goodfellow. He's the guy who invented GANs, or discovered GANs.
Is this where that Facebook story come from, of the two AIs chatting to each other and they came up with their own language because maybe the discriminator went off on a tangent?
Possibly. I don't know if they were using GANs, but could be. Who knows? Yeah. We're far away from what's the Skynet.
In what terms? Computer terms or human terms?
I mean, the state of the art in terms of artificial intelligence is basically maths. It's not consciousness or anything else. Anyway. Right, libraries, TensorFlow, TF-Learn, Keras. At that time, yes. Now, PyTorch is very interesting. The reason PyTorch is interesting is because, well, TensorFlow is somewhat session-based and a black box once it starts running. Okay, PyTorch tries to be more Pythonic and tries to help you in terms of, what's it called, adapt the network as things are being trained. Okay, PyTorch is a kind of friendlier programming model. But the problem was before, PyTorch, it was good to experiment with, but then you'd have to take whatever model you've created and convert it into Keras or something that was more low level for execution in production. With PyTorch 1.0, what they've effectively done is they wrapped the second phase, so you can basically take your nice PyTorch code and just run that in production, which is incredibly powerful to do. They were supposed to release PyTorch 1.0 at the end of summer. There is a PyTorch conference on the 2nd of October. So no definitive, they haven't announced anything yet, but good money could be on them releasing it on the 2nd of October. But PyTorch is worth looking into, as well as TF-Learn. I don't really code TensorFlow low level. I typically use TF-Learn. Some people use Keras, but simply because the amount of work you have to do for TensorFlow is incredible, whereas TF-Learn makes it all simpler. There's a kind of debugging tool called TensorBoard, where you can basically, when your things are executing, you can go in and see how things are performing. A complaint of neural networks is that they're black boxes and they're very hard to reason about. Even with TensorBoard, they're still hard to reason about, but at least you can see if certain weights have got stuck or not, and that sort of stuff. So if you're using TensorFlow, TensorBoard is worth looking into. Implications, where is this going? Yeah, as I said, this is not Skynet by any means. The bigger concern is AI taking over jobs and everything else. Realistically, probably creating more jobs as well as getting rid of old jobs. I mean, jobs evolve. How many people code ASP.NET 1.1 now? How many people code ASP.NET 1.1 now?
Now? Not if I can avoid it.
Well, London banks. But realistically, you'll see a lot of kind of jobs that humans do will effectively go away. But at the same time, a lot of jobs will be created because, well, there'll be a need for it. I mean, at the end of the day, these things are built by humans, not by machines themselves. When that happens, then Skynet might be a, Right, that's it. So.
Thank you very much, Ashic.
Ooh.